So it's 8 o'clock. It's time to get started with our lecture for today. We have two important things to do today. First one is complete the lecture, and the second one is the discussion of the exam. So I brought the exams with me today. So you'll get your paper back, and we're gonna go over the questions, and then we're gonna clarify any doubts that you might have. Um, on Monday, we started our topic on systems within the facility that might affect your layout. When we talk about some of them, the last one was the atmospheric system, and essentially what we did was to discuss how to design for the requirements of an HVAC for both the cooling requirements and also for the heating requirement. So we discussed these two methodologies. First one, to determine the heating requirement of the facility, and we cover the expression and the parameters that were required to compute that specific requirement. And we also talk about how to compute the requirements in terms of the cooling load for your facility. We work on this example, and I was looking at it. One of your classmates called my attention. There's two numbers here that are not correct. Let's see. The first one is the QR. So this number is not correct. The right number should be 3.5 times 10 to the 5 BTU hours. And the second number is the key W. This should be equal to 3.274 to the power of 5 BTU hours. The rest of the numbers are correct. I apologize for that mistake. The way the numbers were computed was correct. The only thing that was different was the final output. So now we're going to discuss an example for the cooling requirements. So we're going to use the same facility that we described on the first example, but we have some additional information to compute the cooling load. So we have some information in terms of the sun location. So the front of the facility faces west, and all the windows and doors have awnings. The lighting within the facility consists of 575 fluorescent luminaries, each containing two 60-watt lamps. And within the facility, we also have some information about the employees that we have to compute the cooling requirements. We have 75 men performing light work and 50 women performing light work. The outside design temperature is 97 Fahrenheit, and the inside design temperature for the facility is 78. So in terms of computing the first, say, 5 of these parameters, we follow the same process that we did for the heating requirement. And then for computing the cooling requirement based on the employees that you have in your facility, you're going to refer to this table. So let's start by computing QF. And QF is the cooling load due to the floor. So we need the area of the floor, and we computed that one on our first example. So that's 25 feet square. And we have the information about U from the previous example. So it's 0.81 BTUs. So this is times 0.81 BTU. Our feet square Fahrenheit. And now you have to remember, now the temperature is different. For the first example, we were looking at 70 and a difference between 70 and 0. Now we have 97 degrees outside and 78 inside. So our temperature difference now is 97 Fahrenheit minus 78 Fahrenheit. And this number equals 3.85 times T to the power of 5 BTU hours. Any questions? So again, QR, this is going to be computed same way we did for the first example. So QR is the cooling load due to the roof. So we need to compute the area for the roof, which is going to be the same area of the floor. So we have 25,000 feet square times the UR for the floor, 0.20. So that's 0.2 BTU hours feet square Fahrenheit. And again, the temperature difference is 97 Fahrenheit minus 78. And that equals 0.95 times 10 to the 5 BTU hours. So for QG, QD, QW, since it's the same process that we follow for the previous example, I'm just going to give you the result, and we're going to work with the rest of the problem. So QG equals 0.06 times BTU hour. QD equals 0.02 times 10 to the 5th BTU hour. And QW equals 0.88 times 10 to the 5th BTU hour. So you follow the same process that we followed for the first example. The only difference is going to be the temperature difference. Yes.
Can you discuss
Yes, that was for this example. So here we're computing the heating. Yeah, temperature change. Any other question? So the only difference in the way we computed these requirements for QRTD to QD and QW is the temperature difference. Now you need to change that and get the results for the cooling. But now we're gonna go to QB, which is computed differently. Actually, so QB is the cooling load due to ventilation. So we're gonna need the areas like we did for QI here. Yes. So the ventilation is gonna use the same areas as the infiltration. So remember, is the area for the roof and the walls. So for that we have 25 feet square plus 12,600 feet square times 0.2 BTUs hour feet square Fahrenheit times the temperature difference. So 97 Fahrenheit minus 78 Fahrenheit. So this equals 1.43 times 10 to the 5th BTU hours. Okay, so now we move to the new parameters for the cooling. So we have QS, and for this we need to get some extra information for the location. So QS is a cooling load due to solar radiation. So let me move to the next slide. I think it's gonna be more space. So for this we need the heat absorption. For the west side of the facility, and this is located in Chicago. So this information, in terms of the question for homework or for an exam, I need to provide you with this data. Okay. So for the absorption factor for the west side, of a facility in Chicago is 100 BTUs hour feet square. And for the east, $75 BTUs hour feet square. We also need the shade factor awnings, and that's 0.3. So now we can compute the factor for the heat absorption. So remember, we have four times 8 double pane glass windows and 3 times 8 glass doors located on both the back side and the front side of the facility. So those are the areas that we're going to need. So QS is 8 times 32 feet square plus 2 times 24 feet square times 100 BTUs hour feet square Fahrenheit. And we're gonna also multiply that times the shade factor. So that's for one side. For the other side, we have 8 times 32 feet square plus 2 times 24 feet square times 75 BTUs an hour feet square times 0.3. So all this equals 0.16 times to the 10 to the 5th BTUs an hour. So there's another 2 things that we need to consider now. The first one is the cooling requirement or cooling load from the lights. So how much load we need to cool the facility when we take into account the heating from the lamps, and also the heating provided by the personnel, the people inside the facility. How are we accounting for that heating, and how does that affect the load? So for the cooling load for the lighting, we have the following expression. QT we have, or we are considering fluorescent type of lights, and that's part of the description of the problem. And we have an expression to compute this specific requirement. It's right here. So we need the fluorescent wattage, and we need to multiply that times 4.25. So for this problem, this is actually should be QL. So for this problem, we have 575 lights that contains 2 light bulbs, okay, containing 2 60-watt lamps. So that's why we have 575 times 2, and there are 60 watts per lamp. So that's the information we need for this portion. So it's 575 times 2, because there's 2 lamps, and the watts are 60 watts. And then we multiply that times the constant, which is 4.25 BTUs hours watt. And this equal to 2.93 times 10 to the 5th BTUs an hour. Finally, we get to the requirements for the personnel. So in that case, we're going to use the table that we have on slide 32. Let me show you that table one more time. This one. So depending on the type of worker that you have within your facility, then you can use these estimates to compute the heat gain for your facility per employee. So in our case, we have 75 men performing light work and 50 women performing light work. So we're going to use the estimate for men 800 and women 700. So let me put that here with the aid of table slide 32. The cooling load from personnel is QP 75 men times 800 BTU hours plus 50 times 700 BTU hour, and that is 0.95 times 10 to the 5th BTUs hours. And finally, now we add all those totals in order to get our total cooling load. So we need to add all these components. And when you add those components, the cooling load QC equals 9.94 times 10 to the 5th BTUs and out. Okay, so how this will help you to design your facility. Now you know the cooling load that you need for your facility, so you can estimate the size of the equipment that you're gonna use to provide that load. And based on that, then you know you need to specify now what the space that that equipment is gonna need within your facility, so you can plan for it. And that concludes our first part for this lecture, which we were looking at some of these systems and how do they affect the layout of your facility. So we talked about these first three. Now we're going to transition to these two, electrical and lighting systems and life safety systems. And after that, then we're going to discuss our exam. Any questions?
Actually,
Yes.
so we added up everything from the ones we were doing last time all the way.
No. That's a good question. I want you to get confused. So this one was for the heating load. So here we were looking at the heating component. And the heating load is right here. So this is a separate problem. Here we are looking at the cooling load. Okay? So when we add the components required for the cooling load, then this is what we get. And this is the load due to the cooling for your facility. Okay, so there are two separate things. Good question. Any other question? Okay. Okay, so this is we're continuing our lecture from part one. So now we're going to look at electrical and lighting systems and life safety systems. And just to remind you, we need to understand as facility planners the various elements or systems that are within the facility, because we need to plan for them when we are designing our layout. But the purpose of this lecture is not to prepare the facilities planner to design the structure or the heating, the ventilation of the facility. It's just to have that in mind when you are trying to come up with your design in your facility, because you know all these elements are going to occupy some space. So in terms of the electrical and lighting systems, the facilities planner responsibility is to specify what level of service is required and where is it required. And as I mentioned on Monday, there will be some areas of your facility that will require more illumination than others. So those are the things that you need to plan for. The power company needs the electrical load requirement for a facility before the construction begins. So that's why it requires a facilities planner to have a good estimate. Which is going to be preliminary. Okay, so you're going to have this estimate and you're going to provide that to the power company so they can design the system that will put electricity into your location. And that will involve several things. The facilities planner must ensure that the major load requirements for both the present and the future are included in the design data. So this is not just designing for right now. You also need to take into account what are the future plans for the company. And right now there's a lot of companies moving into the green type of electricity systems, such as solar panels, wind turbines. So if that is in the plan of your facility, then you have to take that into account as well. So using this information, the design engineer can adequately size mains, switchgear, transformers, feeders, panel boards, and circuits to handle the future electrical needs of the facility. And there's some averages here in this table, just to give you an idea of the typical load requirement for plants, office buildings, hospitals, and so on. So the estimates, at least for 4 of them, are based on the area of the facility. But for hospitals, it is based on the number of beds that the hospital has. So on average, the hospital could be 100, 150 within that average. So that will be the estimate that you're going to use to plan for that. Facilities lighting should be planned by the same person planning the electrical. Should not be planned by the same person planning the electrical services, because illumination should be custom designed for the areas within the facility. So this goes back to the areas that if you're doing some specific operations requiring, let's say you're assembly a very small electrical component or product, you might need more lighting in your area. But if you're managing, let's say, a warehouse or other type of area in which you don't require that much lighting, then the requirements will be different. So we have an 8-step procedure that we can follow to design lighting systems, and I'm going to walk you through this 8-step process. First of all is to determine the level of illumination. So the minimum levels of illumination for specific tasks are given in table 2. So let me show you here this table. Hopefully this table is also available in your textbook, so if you cannot read from it right now, you might refer to the table that you have in your textbook. So this gives you per task what will be the minimum illumination level in terms of foot candles. That's the measurement that is followed for this particular type of lighting. So let's take one example. So if you're looking at the machine shop and you're doing some type of rough bench and machine work, then the requirements will be about 50 foot candles. And this is what you're going to use as a estimate to start planning for your lighting system. These are standards. They're prepared from agencies that take into account the level of stress on the other type of things requiring for the employees. So we need to use these standards for our design. So let me go back here. So when selecting the level of illumination for a particular workstation, the following criteria must be considered: nature of the task, the amount of reflectivity of the workstation, components, and surrounding areas, the current level of natural or general lighting, the need for natural illumination, and the worker age and visual acuity. Step number 2 is to determine the room cavity ratio, RCR. So the RCR is an index of the shape of a room to be lighted. So we're going to look at how the room is designed. The higher and narrower a room, the larger the RCR, and the more illumination needed to achieve the required level of lighting. So we can compute this RCR ratio using this expression. When I refer to equation number 1, I'm referring to the RCR ratio. Another ratio, the ceiling cavity ratio. So this takes into account when you have this lamp hanging from the ceiling, that space that is between the lamp and the ceiling is creating some shaded areas. So if illuminaries are ceiling mounted or recessed in the ceiling, then the reflective property of the ceiling will not be impacted by the luminaries mounting height. So this ratio is not considered. But the greater the distance from the luminaries to the ceiling, the greater will be the CCR and the reduction in ceiling reflectance. So the CCR might be calculated using this expression. So this is our second ratio. And we're going to use that information that we got from the first step. The RCR, from the second step, the RCR is also part of this equation. Step number 4, determine the wall reflections, WR, and the effective ceiling reflectance, ECR. The WR and the base ceiling reflectance values can be obtained from table 3. So here we have, depending on the materials that are used in your room, you can determine what is the approximate reflectance. If the luminaries are to be ceiling mounted or recessed in the ceiling, the ECR is equal to the BCR, which is what we compute on the second step. And if luminaries are to be suspended, the ECR is determined from the CCR, WR, and BCR using the next table. So if that is the case, we need to take all this information and find what will be the best reflection or WR for our room. And I think we're going to do that with an example. So there's a lot of tables, ratios in this methodology. So that's why I'm going step by step so you can refer back to this when you're working on your problems. So step 5, determine the coefficients of utilization. So this coefficient is the ratio of lumens reaching the work plane to those emitted by the lamp. So it's a function of the luminaries used, the RCR, the WR, and the ECR. And we have some standards here depending on the type of luminary that you're using. So for example, if you have fluorescent lamps in uncovered pictures, we have the spacing, that is or the limit in terms of the spacing. And also we have the information in terms of the ratios. So this is the coefficient of utilization. Step 6, determine the light loss factor. So the two most significant light loss factors are lamp lumen depreciation and dirt that is accumulated in the lamps. So lamp lumen depreciation is gradual reduction in lumen output over the life of the lamp. So typically the lamp lumen depreciation factor are expressed as a ratio of the lumen output of the lamp at 70% of the rated life of the lamp. The lumen output for various lamps are given in table 6, include the lamp lumen depreciation. Therefore, no additional consideration is needed. So we have table 6 here. So depending again on the type of lamp that you have, we can refer to the watts. So let's say we have 60 watt lamp. You can get the lamp output at 70% of the rated lamp. And we also have some information about the dirt depreciation factor. So again, we look at the type of lamp that we have, and now we need to know what's the typical maintenance performed on this lamp, if they're clean every month, or if they are clean every 2 years, and so on. Because that's what's going to give us our estimate. So let's say you're looking at a type of facility like mill offices, paper processing, or bag machining. So now you have the estimate in terms of the number of months that the lamp stays between the cleaning. So if it is every year, then you can get an estimate for the type of lamp. So that will be the output based on the depreciation. So step number 7, calculate the number of lamps and luminaries. So utilize equation 3 to calculate the number of lamps and equation 4 to calculate the number of luminaries. So this is the step in which you're going to say, okay, we're going to need this many lamps in our facility. And then in step 8, we get to deal with the location of these lamps. So for the purpose of this course, I'll get you up to here. So I'm going to ask you to estimate what's the number of lamps. This will require a lot of things, so I will not put you into this step 8. But you need to have an estimate. You need to know how to compute an estimate of the number of lamps that you need for your facility. And here we have an example. So let me see if we can start working on this one. Yeah, we have time. So let's look at this problem. So first, a machine shop, we have the area of this machine shop with a 13-feet ceiling. Will be illuminated for automatic machine and rough grinding. Uniform lighting is required throughout the machine shop. So this is telling us that we are not going to have areas with different type of lighting. All the facility will have the same lighting requirement. And if the luminaries are to be ceiling mounted, so that means that they are not going to be hanging. They're going to be like this ones. All ceilings and walls are to be painted white, and all luminaries are to be cleaned every 24 months. So every 2 years, we're going to perform some maintenance. What lighting should be specified? Okay, so we're going to work on this step by step. Step 1, we need to determine the level of illumination. And for that, we're going to use table 2. and we have an automatic machining and rough grinding facility. So based on that, based on this information, we can go to table 2. And find out which of these describe the type of facility that we have. So we have a machine shop in medium base and machine work, pneumatic machines, rough grinding. So this is the description that matches our facility. So in terms of the minimum illumination level, we will have 100-foot candle. So go here. So we need level of 100-foot candles. Step 2, determine the room cavity ratio. So this is going to consider the space between the lamp and the surface for the working area. So the problem is not stating what's the height of the tables that we are using or the stations that we are using. So we are gonna assume that all working surfaces are 3 feet from the floor. Okay, so our workstations are going to be elevated 3 feet from the floor. So to compute the room cavity ratio, we go to the RCR ratio, step 2. It's right here. So we need the height from the working surface to the luminaries. So this is a 13 feet height facility. So we're going to subtract that from 3, and that's going to give us the height from the working surface to the luminaries. And then we have the room length, the room width, and same information. So let's compute that here. We have the RTR equals 5 times 13 minus 3 times 100 plus 40 divided by 100 times 40. And that equals 1.75. And remember, we're going to use this ratio for the next step. Bless you. So step 3, determine the ceiling cavity ratio So when we go to step 3, here's the expression that I was saying. We have the RCR ratio here in this expression. But if we go back to the description of this step, if the luminaries are ceiling mounted, then the reflective property of the ceiling will not be impacted by the luminaries mounting height. So we don't need to compute this ratio. Because in our case, in this problem, our lights are located on the ceiling or ceiling mounted. So for step 3, the CCR need not to be considered as luminaries are ceiling mount. Step 4 is to determine the wall reflections and the effective ceiling reflectance. So for that we need to refer to table 3. And we're going to look at a facility with white paint, light color paint on. Specifically, we have white paint in our description, so the approximate reflections will be 80%. So WR and VCR are 80%. And because the luminaries are to be ceiling mounted, the ECR is also 80%. Questions? Okay, so we have WR, VCR.
And the ACR.
So we are almost done here. Step I think I'm gonna stop here and we're gonna start passing the exam. I want to have at least 15 minutes to discuss the questions. So we'll continue from here on Monday. You have a homework chance to look at tracks